It's okay, very good. So we listen now to Professor Glueck from the University of Passau, Germany. He will present us Perron-Frobenius theory revised, spectral properties of eventually positive operators. So welcome, Professor, and you can start.
Thank you very much for the kind introduction, and I'm very grateful to the organizers of this conference for the opportunity to speak here today. Yes, so I want to revisit an old topic in the theory of positive operators, namely Perron-Frobenius theory, or the so-called spectral theory of positive operators. And I want to present certain generalizations to you, namely, instead of positive operators, we are going to consider, after a few slides, eventually positive operators, whatever this means. So let's see. Let us start with a brief reminder. In finite dimensions, positive matrices. Okay. So let us consider a D times D real matrix, square matrix, which is entry-wise non-negative. And well, I'm going to use the following terminology. I call this property of T positive. There are many people who would call it non-negative. Depends a bit on which community, who you ask. Yeah. So let's call this matrix positive because it fits very well to the infinite dimensional terminology. Okay. So entry-wise non-negative means positive in this terminology. And I'm interested in spectral properties. What I have defined here is the spectral radius of the matrix, which is you take all lambda in the spectrum of T, which is denoted by sigma of T here. And then you take the absolute value, the modulus of all this lambda, and you take the maximal modulus of all eigenvalues, all spectral values. This is the spectral radius. Okay. And a second very interesting, let's say, entity or quantity is the so-called peripheral spectrum. The peripheral spectrum is the set of all spectral values of T, which have maximal modulus. Yeah? So all lambda whose modulus is equal to the spectral radius. And throughout the talk, I'm going to be interested in those two properties, mainly in the second one. Okay. Now here's a very old and classical theorem of Frobenius, actually. Part of the Perron-Frobenius theorem. First of all, the spectral radius is itself a spectral value. And this is a consequence of positivity. It's like from 1911 or so. It's more than 100 years old, this result. And we can also say something about corresponding eigenvectors in finite dimensions. So it's not only an eigenvalue, the spectral value, it also has a positive eigenvector. So x, which is entry-wise non-negative and non-zero. You can find such an eigenvector x for the spectral value R of T. And also for the dual matrix, by just taking the transposed matrix, you can also find a dual eigenvector, which I called y here, which is also positive, which is an eigenvector for T transposed for the spectral value R of T. Okay, so this is part of the very classical Perron-Frobenius theorem. Okay. The spectral radius is also the spectrum. That's what I wanted to say about the first quantity here. You can see my mouse? Yeah. Well, I hope you can see the mouse, okay. So what is a bit more interesting is the second quantity, the peripheral spectrum. Now, in order to show you what happens with the peripheral spectrum, I first start maybe with a little example. So I have here the complex plane, and I mark the complex unit circle in gray here on the right. Now consider a very simple matrix, a 3 times 3 matrix, which is just a cyclic permutation matrix here, 3 dimensions. Okay. Now we can compute the spectrum of this. This is a positive matrix. You can compute the spectrum of the matrix, and it's precisely those 3 blue points here on the right. And it's the third roots of unity out of the spectrum of this matrix. Okay. Now I'm going to check. That's quite interesting actually, because here the spectrum is equal to the peripheral spectrum. Yeah, so the spectral radius is 1. The peripheral spectrum is those 3 blue points. So it's actually a subgroup of the complex unit circle with respect to multiplication. Now I'm going to modify the matrix. I make it a 5 times 5 matrix. I just copy the blue matrix and I added, it's a direct sum, another permutation matrix in 2 dimensions. Now, if I compute the spectrum of those of the red matrix here, then I get the point, well, 1 and -1. So the spectrum of the entire matrix is now marked in blue and red here on the right. And we have the 3 blue points and the 2 red points, and one of the red points on the right coincides with the blue point, namely the point 1. So actually we have this union here on the right of the blue and red set as peripheral spectrum. The union is no longer a subgroup of the unit circle, because if you take the upper blue point and the right point, here the red one, and you multiply them, then it's none of the other points, and so it's not a subgroup. But it's a union of subgroups, and that's actually what I'm up to. So here's a theorem also due to Frobenius actually. The peripheral spectrum is, well, let's say we normalize the spectral radius of our positive matrix to 1, just to make the statement easier. It's just a normalization. Then the peripheral spectrum is always a union of subgroups of the complex unit circle. That's a consequence of positivity. So not just for permutation matrices, but always. Okay. Now this is classical Perron-Frobenius theory. Now probably we would like to see something in infinite dimensions. So here's the infinite dimensional result. First of all, no, that's not infinite dimensional yet. I copied the finite dimensional statement from the previous slide. So the statement was positive matrix T with spectral radius 1. Then the peripheral spectrum is a union of subgroups of the unit circle. Now I'm going to modify things here. First, I modify the first line here. Instead of a matrix, I now consider that T be a positive operator on a Banach lattice, infinite dimensions in general. Okay, well then I need to change something in the theorem. I added in blue here. In addition to the spectral radius being 1, I need a growth condition on the operator. For instance, I need a power boundedness of the operator. And so for instance, if it's contractive or if powers are uniform, norm bounded, then indeed the same assertion remains true. Again, the peripheral spectrum is a union of subgroups of the unit circle. This is a result which is more than 50 years old, actually, due to Lotz from 1968, proved by an ultra power technique. Okay, so that's an infinite dimensional version of the Perron-Frobenius theorem. Now, I have an open problem for you. It's one of my favorite open problems and one of the most notorious open problems in positive operator theory. You can find it, for instance, also in the very interesting survey by Professor Krobler, who is here today. I think more than 20 years ago, he has written a survey about infinite dimensional Perron-Frobenius theory.
Your mic is muted.
Sorry, somehow I was muted. Don't know why. Okay, let's try again.
Professor Glueck, we don't see your screen.
Yes, something went wrong, but I think you can see it now again.
Yes, it's okay now.
Okay, great, thank you. Okay, so sorry, don't know what happened. Let's go on. So this was also in the survey, but it's still unsolved, as it's what I would call the cyclicity problem. So the question is, consider the above theorem, and we have this blue growth condition here. And the question is, can we actually can we drop the growth condition? So is it true without the blue condition? So in general, is the peripheral spectrum always a union of subgroups of the unit circle for every positive operator on a Banach lattice with spectral radius 1? That's the question, and it's open. So I spent quite a few hundred hours during my PhD thesis about trying to solve the problem, but I still have no idea how to solve it. Maybe somebody else has an idea. Okay, so that's the cyclicity problem. Why cyclicity? Well, the property of being a subgroup, a union of subgroup of the unit circle, is sometimes called that is a cyclic set. Yeah, a cyclic set is a union of subgroups of the unit circle. So I call it cyclicity problem. Okay, now one thing is interesting here. one should be a bit cautious. I assumed here that we consider an operator on a Banach lattice. There is, of course, a more general concept of ordered spaces. For instance, you can consider ordered Banach spaces without lattice structure. Yeah? And you might be wondering, well, maybe the same is true there, the theorem belongs. But no, it is not. The lattice structure is very essential, and I have an example here for you. So the theorem does not hold an ordered Banach spaces, which are not lattices, and I have a three-dimensional example, actually. So one of my favorite cones, which is not a lattice cone, is the ice cream cone in 3 dimensions. I have a picture here. R3 with the ice cream cone. And I consider the following operator T. So T is a matrix which is a rotation of the space about the symmetry axis of the ice cream cone by angle theta. Yeah. And now, so here's the picture. I have angle theta, and I rotate the entire space by this theta. Now, obviously, this rotation leaves the ice cream cone invariant. So this means actually that it's positive, the rotation here. But you can compute the spectrum of this operator T. Well, so the point 1 is in the spectrum, always, again, due to the positivity. And the other 2 eigenvalues are a complex conjugate pair of numbers, namely 2 complex numbers on the unit circle with angle theta and minus theta. Yeah, those 2 here. So this means by such a construction, I can achieve any 3-point set on the complex unit circles, which consists of the number 1 and of a complex conjugate pair of numbers, and I'm able to define the angle as I would like to do. Yeah. So it's not in general a union of subgroups of the unit circle. So it's really about the lattice structure. Okay, now let me go ahead. This was about positivity in the first 2 slides. Now let me speak about eventual positivity. What is that? Well, let us start in finite dimensions again. Okay. So a matrix is called eventually positive if, well, not t, but t to the power n is positive for all sufficiently large integers. And so let's say from all n larger than 10 on, the power t to the n is positive, then I call the matrix eventually positive. Okay. Now I think it's good to have a little picture here to gain some geometric intuition of what this means. Well, of course, that a matrix is positive means if I start with a vector in the positive cone, and I endo RD with a standard cone again. If I start with a vector in the positive cone and I apply the matrix, then I remain staying within the positive cone. Yeah. And eventual positivity means, of course, that if I start with a positive vector and I apply the matrix sufficiently often, then I end up in the positive cone again. But I might not stay in the positive cone for small powers n, for small exponents n. Okay, so here's a picture how this could look like. Let us again consider the 3-dimensional Euclidean space. That's R3, as you can see. Let us consider the standard cone. So I marked parts of the boundary of the standard cone here in gray to get a bit more intuition of the geometry. And what I do now is I consider a rotation about an axis in the middle of the cone. So this blue axis here, let me draw it. That's a blue axis somewhere in the middle of the cone. And now t should be a rotation about this axis, but what I call a compressed rotation. So it's not just a rotation, but it now becomes closer and closer to this axis. And so it spirals down towards the axis. That's my t. Now let us consider an element in the positive cone, which I call x0, and I want to draw the trajectory of x0 under the powers of t and see what happens. Okay, so here's one instance of a number in the cone. It's in the boundary of the cone because then the picture is a bit more interesting. Called x0, and now I apply t and then t squared and so on. So I'm in the cone, but tx0 is not in the cone. Apply it again. I'm still not in the cone, and I'm somewhere below the cone here. Once again, now I move back in the direction of the cone. I enter the cone again, and I stay within the cone, and the spirals towards the blue axis. And so this is what happens. And if I go on and go on, it converges to the blue axis, and it stays within the cone. And you can draw the same picture for every positive initial value x0. And so it always stays within the cone if time is sufficiently large, but not for small times in certain cases. Okay, that's eventual positivity in 3 dimensions. Now, when we can show results about positive matrices and operators, natural to ask, can we also show the same results for eventually positive operators? So once again, the peripheral spectrum, but this time in infinite dimensions. So I've copied the result from 2 slides ago here. The result of lots about positive operators on Banach lattices. T is a positive operator on a Banach lattice, and the result of lots says if T has spectral radius 1 and T is power bounded, then the peripheral spectrum is a union of subgroups of the unit circle. We already discussed this. Now I want to change the result. I first want to change the first line here. Let's now consider an eventually positive operator. And what do I mean by event? Well, actually, I wrote uniformly eventually positive. Okay, what do I mean by this? Well, I mean again that T to the power n is a positive operator for all sufficiently large exponents. Okay. Now, why do I need this word uniformly here? Well, in infinite dimensions, there is indeed also another version of eventual positivity, which I'm going to discuss in 2 slides. So just for a moment, it's the same property as before in finite dimensions, but I just use the word uniformly, and I'll explain later why it's reasonable to add the word uniformly here. But it's the same property as before. Now, what happens to the theorem here? Okay, well, the answer is nothing. It's still true. Just have to replace the author. And so I proved in 2017 that it remains true under those assumptions here. But I really need power boundedness. Lots has a slightly less restrictive growth assumption for positive operators. I don't know if this works for eventual positive operators. But so for power bounded operators, it works. Okay, so that's the theorem. Okay. Now, if I were you in the audience, honestly, I would think, so what? And so, okay, it's true for positive operators. So now Glueck came here and tells us, oh, it's also true for eventually positive operators, most likely with the same proof, right? So everything's trivial. So it's just another technical generalization of some old technical theorem. No. The point is, one can't use the same proof as for positive operators. That's one of the interesting points here. If you have a look at this classical proof of lots from 50 years ago, he somehow lifts the operator to an ultra power, and then he turns spectral values into eigenvalues and argues with the eigenvalues. And at one point, in order to make those arguments work, he needs to factor out a certain invariant ideal. At some point in the proof, this occurs, and it's very important to do this because otherwise the entire structure of the proof breaks down. Now, if you try to copy the same argument for eventually positive operators, you can write everything down, everything is well defined, but this ideal which you have, it's no longer T invariant. And then the entire proof breaks down. So one of the interesting things here is that although the statements are very similar, the proof doesn't work. So we need something else. And of course, mathematician, I'm happy if the proof doesn't work in a more general setting, because it means that I need to do something new. So here's a sketch of the proof. Here's just a very brief sketch. Proof idea. We consider a sequence of integers which converges to infinity. For instance, the integers themselves or something else. Any sequence. Now I lift the problem to a sequence space. By L infinity and not E, I mean the space of all E-valued sequences. That's also a Banach lattice. Okay. And on this space, I can consider an operator. Let's call it a S. And S acts as follows. It takes a sequence, x0, x1, x2. So those are points in E. And it maps them to T to the first integer here, k0 times x0. T to k1 times x1, T to k2 times x2. Okay. Now, if you have a look here and say, well, if all those x1, x2, x3, and so on, if all those are positive, then due to the eventual positivity of the operator, this means, well, all those need not be positive, but they are positive for sufficiently large powers, or if you're sufficiently far on the right. Okay. Now, what you can do, you make a so-called ultra power construction. From this space L infinity with values E, you factor out all null sequences, all sequences that converge to 0 along a certain ultra filter in the natural numbers. So I'm not going to discuss which ultra filter we use, but you can factor out null sequences. But if you factor out null sequences, this means that everything that happens for finite time just doesn't matter anymore. Yeah, it's just completely irrelevant what happens for finite time. Right. Okay. So if I factor out those null sequences, I get another induced operator. I call it S hat here. But this is no longer defined on L infinity. It's defined on L infinity modulo the null sequences. And L infinity modulo those null sequences is so-called ultra power of E, which I denote by e to the u here. And this induced operator S hat is positive on this ultra power. Yeah? So the null sequences are in an ideal in the Banach lattice L infinity. So the factor space is also Banach lattice. It makes sense to talk about positivity here. So this is positive. Okay. Now the problem, of course, is that this operator S hat, well, it's related to T, but its spectral properties might not be related to T, at least not so closely, because we have all those powers here. So what do we do now? Okay, well, consider the fixed space of S hat. Fixed space is the eigenspace for the eigenvalue 1. All x such that S hat x is x. Well, now the fixed space of positive operators has the property that it's often, let's say often, a sublattice of the given Banach lattice under certain assumptions. Strictly speaking, this is not true. Though I wrote almost a sublattice, you need to do a few technical constructions to ensure that it works. But I don't want to go into those technicalities. So we can assume that it's a sublattice. It's a sublattice. After some modifications, we get that a fixed space is sublattice. Okay. Now, and the interesting thing is that I can also lift my operator T to the ultra power EU, yeah, because T also acts on L infinity with values in E. I just applied T to each component, then I have operator in L infinity, and then I factor out the null sequences again. Then I have lifted T to the ultra power EU. And the point is, if I restrict this lifted operator TU to the fixed space of S, then it suddenly becomes positive. Why is this true? Well, it's true because of the following equality here. On the fixed space of S hat, on the fixed space of S hat is the identity. And so I can just write it there. So TU is the same as TU S hat if I apply it to elements of the fixed space of S hat. So it's just the same there. But the point is that, you see, so S hat is essentially given by this operator here. And then I multiply it with T once again. So what happens here is I get T to the K0 plus 1, T to K1 plus 1, T to the K2 plus 1, and so on. So again, increasing powers, but the operator is eventually positive. So those are positive from a certain point on. Yeah. And this means, since they're positive from a certain point on, if I again factor out the null sequences, it becomes positive. So this product here is positive on the ultra power, but on the fixed space of S hat, it's the same as TU. And so TU is positive on the fixed space of S hat. And then you're essentially done, because you now have a positive operator on, so I modified T to TU restricted to the fixed space of S hat to this operator. And this operator is a positive operator in the Banach lattice, and I can apply lots result there. And the only thing I need to make sure that everything works is that the spectrum of T is close enough to the spectrum of this modified operator. And you can do this by, let's say, choosing the sequence Kn appropriately, then it works. Okay. Yes. Great. So, what's the time? Nice. Okay. So I have one more thing here. Riesz points. There's another very interesting theorem about the peripheral spectrum of positive operators. T is positive for the moment on a Banach lattice. And here's a theorem by Niro and Sawashima, even a bit older, from 1966. The theorem goes as follows. If T has spectral radius 1, and in addition, the spectral radius is a pole of the resolvent, the spectral theoretical property, and the spectral space, which corresponds to this pole, so the range of the spectral projection, this shall be a finite dimensional. And that's my assumption. It happens very often. So this is a name. This property is called the Riesz point of T. The Riesz points are poles of the resolvent with finite dimensional spectral space. And the theorem says, if the spectral radius is a Riesz point, then every other value in the peripheral spectrum is also a Riesz point automatically. So somehow this Riesz point condition from the spectral radius is it somehow gets transferred to the rest of the peripheral spectrum automatically by the positivity. That's an old result for 55 years by now. I want you to talk about eventually positive operators, of course. So I modified the first line now and replaced positivity with the blue condition, uniform eventual positivity. The question is again, what happens to the theorem? Well, I need another assumption, which I added in blue in the blank line here. I again need, I think yes, we need that also, at least for the proof, we need that T is power bounded. And if we add this assumption, then the theorem is the same. This was proved by Sahipa Arora, who is also in the audience today, and by myself. The most recent version of the preprint is from this year. And then it stays true, yeah, for power bounded operators. We actually don't know whether it stays true without the assumption that T be power bounded. Why don't we know this? Well, again, the old original proof techniques by Niro and Sawashima, and also by Lotz and Schaefer, they also gave a proof. They don't work any longer in the eventual positive setting. So we need something else. And the something else works in the power bounded case. Okay, let me see. Good. Those were the Riesz points. Now I promised you to briefly speak about the word uniform. Why did I introduce the word uniform here? So let us again consider a bounded linear operator and a bounded lattice. And I showed you the word uniformly eventually positive in the previous slides. Yeah. Let us recall how I defined it on the previous slide. So it's called uniformly eventually positive if, now I wrote it by using quantifiers a bit more formally, there exists and not such that for all subsequent exponents n, the operator t to the n is positive. That's uniform eventual positivity. Let us rewrite this assertion in a slightly different form, which is still equivalent. The equivalent formulation is, I use vectors to write it. So this condition, for each n from n non on, the power tn is positive means that it maps positive vectors to positive vectors. So I can rewrite it in this way. There exists and not such that for all positive vectors f, and for all integers n from n not on, t to the n f is also a positive vector. That's just the same, right? Now let me take the letter assertion here. Let me copy it. I copy it for you. Here's the same, but I marked two quantifiers in color, in blue and red at the beginning. It's just the same statement. Now what I'm going to do is, I'm going to swap the quantifiers. Swap them. Now I have a weaker statement. Now I have a statement that for each f, there exists a time n naught, such that from all subsequent times for exponents n, t to the n f is positive. The point here is that this n naught is now allowed to depend on f. Yeah, it's allowed to depend on f. So this is a weaker statement, and this weaker statement gets a name. We call it individually eventually positive, because the n naught somehow is individual and depends on the f. Okay, so that's why in finite dimensions it's easy to see that this is the same, it's just equivalent. But in infinite dimensions, they're not the same. So in a paper with Daniel Danners and James Kennedy from 2016, he constructed an example on the space of continuous functions from the interval -1, 1. It's not very difficult, where you can see that uniform eventual positivity is really stronger than individual eventual positivity. Actually, we gave a semigroup example there, C0 semigroups, but the same construction works for operators too. Okay, let me see. Great. So 30 minutes are over. I showed you as promised why we need the word uniform. That's the end of my talk, and thanks a lot for your attention.
So thank you very much, Professor, for this interesting talk. Are there any questions or comments?
Yes, I have a question.
Yes.
Hello, Jochen. You know, on the Banach space case, Katznelson and Zafiri has some results about the peripheral spectrum and some kind of 0-2 law for the power-bounded operators. And so on, they have also some ergodicity results about power-bounded operators on Banach spaces. But now you are on Banach lattices, and you have uniform or even individual eventually positivity. Do you have any further result about ergodicity or polynomial mean ergodicity, or even you have the continuous part? You mentioned about the discrete. You have just T, and if you have a semi-group case, TT, do you have also any results about peripheral spectrum and related with the ergodicity of it?
Okay, so I think those were two questions. I try to answer both. The first one is, so for instance, one of those results by Katznelson and Zafiri says so t to the n minus t to the n plus 1 converges the norm to 0 if and only if the peripheral spectrum consists of 1 only, right? Or is empty.
Yeah, right.
So, and you can use this, for instance, to prove for eventually positive operators a version of the 0-2 law, which was shown by Professor Muhamedov yesterday. But it's not precisely the same. What you can show is that you have a uniformly eventually positive operator, and then you can say those powers t to the n minus t to the n plus 1, they converge to 0 in operator norm if and only if there exists an n such that this difference t to the n minus t to the n plus 1 in norm is smaller than square root of 3.
Okay. Yeah.
And the point is, by the way, the same is also true for positive operators. And yesterday in the talk, we saw that it can replace square root of 3 by the larger number 2, which gives a stronger result for positive operators, but only if you replace the norm with the regular norm in Banach.
Yes. Yeah.
But if you just take the norm instead of the regular norm, it remains true if you replace 2 with the smaller number, square root of 3, which is about 1.7 something. And then it's also true for eventually positive operators. This follows rather simply from Katznelson, Zafiri, and the cyclicity. So you can do something like that, yes. You also asked about a time continuous case.
Yes.
Yes. Actually, I'd argue that the time continuous case is more interesting than the time discrete case. But I didn't want to talk too much about the zero same group today, though I didn't have it in the talk. So, in fact, our motivation to start developing this theory was evolution equations, linear evolution equations, where eventual positivity really occurs for a lot of concrete evolution equations. So we studied eventually positive zero semigroups, and then you can try to prove similar results. One problem is, so for positive semigroups, a cyclicity result for the peripheral spectrum is known. Then it's so peripheral spectrum is a line now, and it's say the spectrum down to 0. Then it's a union of subgroups of the additive group of the imaginary axis. Yeah, that's for positive semigroups. It's a result due to Greiner from the 1980s, which is an adaptation of Lott's result to the time continuous setting. And we try to do this for eventually positive semigroups too, because it's important in order to understand the long-term behavior of eventually positive semigroups. But we weren't able to prove it. Now, what you can do, and I did this with Sahiba Aurora this year, what you can do, you can use this result for the single operator here, and under certain assumption where you have a spectral mapping theorem, you can use it to prove results about the spectrum of the semigroup, and then you can study the long-term behavior of eventually positive zero semigroups. Yeah.
Okay, I see. I have one more question, if I am able to ask. Is there any relation with, for example, quasi-compactness or eventually compactness? I don't know.
So indirectly. So it's So of course there are eventually positive operators which are not quasi-compact, but there is, you see, if you, for instance, try to characterize eventually positive semigroups, which is important in order to show for concrete evolution equations that solutions are eventually positive, then you need additional assumptions. So what we typically call domination assumptions or smoothing assumptions.
Right.
And if you have those assumptions, there's something like, say you have a semigroup in LP, and the semigroup maps LP into L infinity, and it's a smoothing property. That's what you need in those theorems. It's very closely related to them. So for certain versions, even a characterization. So the point is, those smoothing assumptions, they in fact imply that the semigroup is compact. So there's no direct relation between compactness or quasi-compactness and eventual positivity. But if you have a look at the theorems which we can prove, then somehow those properties meet in the theorems. Yeah. So they are related, but indirectly.
Okay, thank you very much.
You're welcome. Thank you for the question.
Thank you, Professor Baslimas. You can interpret.
Good morning, Jochen. Nice talk. Just maybe a remark. Actually, even in finite dimensions, your talk reminded me of something maybe you thought about. So if you take, you can make sense of irreducibility also if for general matrix which leaves a cone in a finite dimensional vector space invariant. And in particular, you can look at matrices that leave a polyhedral cone invariant, so not just a simplicial cone. Now, if you take an irreducible operator matrix for a polyhedral cone, you still have that the peripheral spectrum are roots of unity. So suppose you take a cone with four, something that slices as a square. Now the question is, what is in the simplicial case? If your cone has dimension n, then the roots of unity have order n. Yeah? And so, or at most n, that's the situation. So, but now what is a good upper bound for a polyhedral cone? And that is actually not known.
Okay. So, by the way, we wanted to mention the property that the peripheral spectrum consists of roots of unities is even true without irreducibility. For polyhedral cones, it's always true.
Yeah, it's always true. That's fine. I agree, but the point is that I want this irreducibility and then find the least number such that all my elements in the peripheral spectrum, if I raise it to the power of that number, it's a unit. It's the unit.
Question.
And this is not known. So if it has to do with the combinatorial structure of the cone, and you need the number of facets of the cone, but also the number of extreme rays. So you need bounds in terms of the number of facets and the number of extreme rays. So anyway, so this is if people are interested in matrices, this is something, but you never thought about this, I guess.
Yeah, so it's closely related to your papers with Onno van Gaans, right? You had similar.
This is never. We never did anything here.
You have this nonlinear paper with the contractions on LP unipose for P is not 2, which is a similar geometric thing, right?
Yeah, well, that is somewhat different than this, I would say. But yeah. Anyway, thank you for your talk.
Right.
Nice talk.
So thanks for your comments. Thank you. I think I should stop because time is over and the next.
So Professor Azouzi wants to interpret.
Just a little question. If the result is false for individual eventually positive?
If it's false for individually eventually positive?
Yeah.
I don't know. Good question. I think I don't know. I don't have a counterexample. I would suspect that it's false, but I don't have an example. If you weaken the property even a bit more to so-called individual asymptotically positivity, which is even a bit weaker, then it becomes false. For individual eventual positivity, I don't know, unfortunately.
Could you please send me the paper about?
Yeah, sure.
Okay.
Yes, sure. I'm gonna send it to you.
So let us thank the speaker again.